We're going to go ahead and take a look at the two-sample problem. Basically, what happens when you're trying to compare two treatments or a treatment to a control group? And this often happens when you're dealing with randomized comparative experiments, where individuals are randomly assigned to one of two treatments, and you want to compare the results of the two treatments to see what happens. Now, when you're doing that, the two samples you're dealing with can be the same size, but don't have to be the same size. So it's not like a matched pair situation where you're comparing individuals of similar characteristics and backgrounds. They can be totally different. Now, we could go ahead and take a look at the data graphically with box plots and stem plots and histograms. However, it would be nice to be able to do something with our test of significance and our confidence intervals, and that's really what it is we're going to focus on. Now, when you're dealing with that, you need to have two simple random samples from your population, could be like men and women, and you don't know the mean and standard deviation of either population. Now, ideally, both populations should be normally distributed. However, if they're for the most part the same shape with no strong outliers, we can go ahead and use the two-sample T procedures. Now, your standard error, which is reflecting your distribution, your how spread out your data is given to you by the standard deviation of your first sample squared divided by the size of that first sample plus the standard deviation of your second sample squared divided by the size of that sample. And then you want to add them together and take your square root. That's your standard error. Basically, that's measuring your variation, your standard deviation of that sampling distribution. Now, when we're using table C in the back of the book, we also need to be dealing with our degrees of freedom. Now, there's going to be two types of degrees of freedom. There's going to be the conservative. If it says conservative, that means you're going to go ahead and take a look at your two sample sizes, and you're going to only deal with the smaller one. And then you're going to go and subtract 1 from that sample size, and that'll be your conservative degrees of freedom. If it does not say conservative or says use software or technology, then we're going to get the degrees of freedom from our calculator or whatever technology we happen to be using. Now, when we're dealing with our two-sample t-test, we're going to assume that our null hypothesis is that the two populations are equal. Now, there's two ways to write this. You could say that the population mean of the first one is equal to the population mean of the second one. Or if you subtracted your mu sub 2 from both sides, you would get this one here, mu 1 minus 2, mu 2 equaling 0. In either case, it both means, or it means that your two populations are equal and that there is no difference between the two of them. Now, with that in mind, we want to go ahead and look at our formula for our t-statistic. Now, it's really the differences in our means from our sample minus the differences in our means of our population over the standard error. The standard error, once again, is what we looked at, this right here. Now, the reason we don't have to have mu1 minus mu2, because it says mu1 minus mu2 is 0, so the second parenthesis is 0, and if we subtract 0, it doesn't change it, so it really just leaves us with the first parenthesis. So it simplifies down to just difference in the sample means over your standard error. And your degrees of freedom, once again, is one smaller than the smallest of the two sample sizes. So let's take a look at this one here. Children are exposed to smoke at a young age in some families, and some families don't smoke. what's the difference in their lung capacity? And so that's what we want to look at. We want to know if children exposed to smoke at a young age have a smaller lung capacity than children that are not exposed to it. So we have the mean for the amount of milliliters of air they can expel. We have our standard deviation, and we have our sample sizes. Here, in this case, our sample sizes are the same size, but once again, they don't have to be. So our null hypothesis is going to be assuming that there is no difference, so the difference between the two is zero, or that they are equal. Whichever way you write it does not make a difference. And this is the mean of the smokers is equal to the mean of the no smokers or non-smokers. Or you could say it's equal to zero. Now, we're going to try to see, we're assuming that the smokers, the children of the smokers, might have a smaller lung capacity than the non-smokers. So that's going to be our alternative hypothesis. We're looking for evidence for that. Or if you would subtract the non-smokers from both sides, you get the mean of the smokers minus the mean of the non-smokers, less than, because it's still that same symbol as we had over here, is less than zero. Now, let's go ahead and take a look at our formula. We're going to go the mean of the smokers minus the mean of the non-smokers. In other words, we're going to assume that the smokers are group 1, the non-smokers are group 2 when it comes to plugging stuff into our formula. So we got to subtract the mean of the smokers minus the mean of the non-smokers, and those are given to us here in our table, over the standard deviation of our smokers, which is that 9.3, over the sample size, which was 30. Now we got to go ahead and put the standard deviation of our non-smokers, all squared, over our sample size. Then we got to go ahead and type that into our calculator and figure it out, and it gives us a negative 3.9 for our t statistic. When you go ahead and use table C, you're going to go ahead and remember that table C, the t being positive or negative is irrelevant, so we're only going to use the 3.9, and it's going to be 29 degrees of freedom because it's always one smaller than the smaller sample size. In this case, they're both the same. So let's pull up table C. Here's table C, and we know our t-value is right here, and we're looking at the positive version. We're also looking at 29 degrees of freedom. So you want to go across your row of 29 until you get a 3.9. When we go across here, 3.9 is really to the right of this one here. So as you go across, your p-value here goes down. So we know since our 3.9 is over here, that our p-value has to be smaller than our 0.0005. And so that's what we're saying with this. Our p-value is smaller than 0.0005. Since our p-value is so small, we then reject your null hypothesis that there is no difference. So it appears that children of smoking parents have a smaller lung capacity than children of non-smoking parents. Now, for the most part, we're going to go ahead and do this with our calculator. Now, we're dealing with a two-sample, we're dealing with a test, a t-test. So we're going to go stats, arrow to the left is test, and it's the two-sample t-test. Now make sure you get number 4, which is a two-sample, and it's a t. Number 3 is when you're dealing with a z. We're not going to be using that one. We're going to be dealing with a two-sample t-test. You then want to go ahead and type your data in here, and you can pause it while you type it in. Now, it says pooled or no, not pooled. You never want to pool. This right here is for your alternative hypothesis. Now, when we look back here, your alternative hypothesis, is what we were dealing with up here. There were two ways to write it, where you had 0 on one side or where you were comparing the two means. Your calculator always goes with the first set, and we're looking at your group 1, the smokers, being less than your group 2, the non-smokers. And so then you want to have your less than mu2 highlighted. Then you want to go ahead and calculate it. And so then we end up getting this screen right here. Now there is an arrow down, and it would display your means and your sample standard deviations and your sample sizes if you arrow down. But we're really concerned about what's on this screen right here. Here's your two sample t statistic, which is a more accurate measure than what we had up here of a negative 3.9, but you realize our negative 3.9 is really pretty close. Here's our p-value, 1.385, and you might realize that, hey, we have a problem with that. Well, yes and no. You know your p-value always has to be between 1 and 0, and that's because we have this here. It just means you got to take your decimal point, which is right here, and move it 4 places to the left. That's what that e to the negative 4 means. So it ends up being a really, really tiny p-value, and that's what we noticed using the table. You could use the table, but whenever possible, use your calculator. Now, we also have the two sample t confidence interval. Well, you need to deal with your t star, which is from table C. So you look at your degrees of freedom, which is once again the smaller of the two. Look at your table C. You find your degrees of freedom here on the left, and then you go across to the column here until it got to your confidence level down here. So if you were looking for a 95% confidence level, and we were dealing with our last problem where we had a sample size of 30, you go across in your 29 until you got to your 95% column, and then this would be your T star that you would end up using in your formula. That's our T star here that we're going to use, and then you'd multiply it by your standard error. And once again, that was this formula here. So your margin of error is T star times your standard error. That tells you how far you would go on each side of the differences in your two means. Now, you can do that by hand, but we'll typically be using our calculator to do this. So let's go back to our calculator, go stat, arrow to the left to test. Now we're dealing with a two sample t interval, so we're going to scroll down our list till we get to a two sample t interval. Make sure you get the t interval here. And your data is already in there from when we did our t-test, so we'll just go down, type in our 95% confidence level. Once again, you never pool, and then we can calculate this, and then it gives you your two sample confidence interval here. That's how we will typically do this. But if you want to do it by hand, you do the differences in your two means, and then you go plus or minus your margin of error with this formula here. Now, a common mistake that people make when they're dealing with a two-sample situation is they'll do a confidence interval for a one-sample confidence interval for their first one and check to see if their second mean falls within this. But that's wrong because of your standard error formula is so much more complicated looking. So we don't want to do that.